BPMN is a modeling language, just like other modeling language like UML, but this modeling language is made specifically to model processes. And one category of BPMN is choreography, and choreography are made to model the interaction between different entities. So let's just describe the components of this modeling language. First, we have an activity, and we have a sender, receiver, and the activity, which is in the middle. So here, for example, we have the customer that is sending the message, and then on the other end, there's a retailer that's receiving the message. And here, it's just the customer is basically placing the order, just like we saw before. Then we have the sequence flow, which come between the activities. And then we also have events. So events is basically when something happens, when the process is getting executed. So for example, we have a timer event that could be a deadline, for example. When it's reached, an activity can be done. And then we have the gateways. For example, here we have the XOR gateway, which is basically just a business decision. For example, here, do we accept the order, yes or no? So let's look again at our choreography. So first, just like we saw before, the customer is placing the order, the retailer, and then the retailer will react to this order by handing over the parcel to the logistic provider, and finally, the logistic provider hopefully will deliver the parcel to the customer. So how do we execute this process? How exactly do we do it? There exist some systems just known as workflow engines, and here some of them, or we can call them BPMS, because we're talking about BPMN. And these engines are specifically made to execute these choreographies. So they're basically process aware. So let's just take a quick look on the architecture of these systems. So we have the modeler, which basically does the modeling of the choreography, just like the one we saw before. And then we have the participant, which basically interact with this choreography through the task list panel. And we have the admins, which does the configuration of the system. Most of the processes are stored in the model repository, and then they get loaded into the execution engine. They get executed, and then the participant will be notified if they have any task to do. So that's basically how it is. The participant has a to-do list, and that's where the models are stored. And also the execution log is needed by the admin for later use. So Camunda is one of these systems. It's very well known. Just a quick example. That's how you model the execution, the process, and then that's a task list, for example. Here, that's how the participants see their task. They can input the data. They can fill the information that is needed for the process to continue. So basically now our process is very simple. We need to extend it a bit. So now we've added this piece of activities. So first now we have the customer, which is querying the available offers, and then is receiving them from the retailer. And now we have an event-based gateway. And basically this is activated whenever we receive a message from the customer. It's either the customer place the order or reject the order. And finally, just like we saw before. So now we've seen how we execute the process, but where does it exactly get executed, right? So we have 3 different parties, but who gets to execute this process exactly? It's not really deterministic. So we have three different options. First, we can rely on one of these parties, which is, let's say now it's the retailer, and then the retailer execute this process. So the downside of this option is that the other parties have to trust this retailer, otherwise it won't happen. And the entire process state is only known to the retailer. They have the option to tamper the data with the state. The other option is distributed. So each participant have a chunk of the process. So it's not really seen, it's not visible, totally visible to all of the participants. So the sum of these chunks will give us the full state of the process. However, in case of a delay or fraud or any problem with the process, the other participant won't be aware of what exactly happened, and they can easily blame each other on the problem. So to solve this problem, we can replicate the state among all of the participants, just like here. So now all of the participants are aware of the state of the process. And that's exactly what is a blockchain network. A blockchain is basically replicated data among all of the participants. And of course, participants can still interact off-chain without using the blockchain network, just in case they had to do so. So now let's just talk about blockchain in general. So in a very simple way, blockchain are just a transaction-based state machine. And so we start from a state. For example, here we have two participants, and then a transaction will change the state of the current state to new state. So, but now let's imagine that we can also have multiple transactions back together instead of one transaction. That's exactly the same thing. So now that's a different view. So first, the customer will submit a transaction, and after the transaction is mined to the block, the state is updated. And that's what a block is. So when we receive a block, we update a state. So what all we need is the blocks. This is the explicit data that we need, and based on this data, we can build the state. So that's exactly what is replicated among all of the nodes that are participating in the blockchain network. So that's how a blockchain network would look like. We have multiple nodes connected together, and they form the network. And inside each node, we have the blockchain replicated exactly as it is for the other nodes. We have a transaction pool with a transaction where we have the pending transactions that haven't been added to the blocks yet. And then we also have a virtual machine inside each node that is totally isolated from the outside world. And inside this virtual machine, we execute some kind of code that will also interact with the network. So now, who exactly propagates the blocks? Who exactly will publish these blocks that will change the state of the network? For this reason, we have something called consensus. Consensus basically is just an agreement among all of the nodes on whom is supposed to publish the block currently. We have two types of agreements, two types of consensus. We have a proof-based and a voting-based. Proof-based, I'm going to assume some of you heard of proof of work, and proof of work basically it's just guessing a puzzle or just a number hash, and then the first node who guess this puzzle will be able to publish the block. While in voting based, it's just we have a leader and validators, and most of the validators have to agree on the block that has to be published. So just a quick description of the consensus. So now we have two types of blockchain network. We have the permissionless, and basically here all the nodes are equal, and the identity is not known to anyone. So we have, for example, Ethereum or Bitcoin as those permissionless network. So here, when we have the clients, they interact with the network. They don't really need to know which nodes they talk to. It doesn't matter, because all the nodes are supposed to be on the same level. We also have the permission blockchain network, and here nodes, we differentiate between them. Each node has different privilege over the other nodes. But of course, there's no centralized node in this. Otherwise, it won't be blockchain network anymore. In that case, the users, the node could be owned by some users that interact with the network, and yeah, unlike the permissionless. Also, it's worth to talk about distributed file system. In distributed file system, basically the user will, so in a blockchain network, it's not really made to store big data. And to solve this problem, we use the distributed file system. And here the user will send the file they need to store in there, and then they receive back an IPFS hash or a CID. And basically the file is distributed among all of the peers in the network. And then with this CID, we can store the CID in the blockchain network, which will point basically to the file which is stored in the IPFS. So blockchain will act like a data registry for the data. So now, how does the user exactly interact with the blockchain? We have 3 different architecture. First, the user can interact directly with a blockchain without any middleman here. And basically, the user are responsible to sign their transaction with a public and private key. Second type is we have the backend, which is in the middle between the user and the blockchain. And here the blockchain basically does the transactions signature for the user. And this is a good solution for enterprise, where we have different multiple users that work in the same organization. And lastly, the users still communicate with the backend, but however, they do the signing of the transaction. So now we have seen the blockchain and we have seen the traditional workflow engine. Now we can take a look at the blockchain-based workflow engine. So that's the traditional one we've seen before. So what we can do is now to partition the system into multiple parts. Each part is going to be located on a different end of the system. So the first layer is front end. So the tool, processing model tool, the task list panel, and the admin tool can be placed on the front end. It doesn't have to be hidden on the back end or the blockchain. So this is really specific to the users. And then with the model repository, we can place it on the IPFS. Since it's a big data, we can't really store that. It won't be efficient to store that on the chain. And then finally, the execution engine will be hybrid between backend and also blockchain. So now we will see this in detail. So that's the first architecture. So we have the front end, we have the modeling tool, task list panel, and then we have in the back end we have the compilers that will does the compiling of the tool of the model of the process, and then it will send it to the deployment mediator, which will basically deploy the process on chain. And then we have the certificates registry, and that's basically where we store the private public key of the users, and we use it to sign the transaction of the users. And yeah, and also we have the event monitor that will listen to the smart contract, to the blockchain, whenever there's an event happening, to let the user know that you have some task to do. That's the first type of architecture we have. The second type is we do the signing on the user side, on the front end. So now we have the execution monitors moved to the user side, and they have their own wallet. Now the user have to deal with the complexity of the blockchain instead of having this on the back end. So now let's talk more about the smart contract. So what exactly we have there, and this is where the process is basically built in. So in the contract, we start with the header. We have the state of each choreography element. It's either disabled, enabled, or done. And then we have the process variables. So here we have the global variables of the process. Here, example, we have the amount that the user might request. We have the shipment address of the user, for example. And then we do the mapping of string to address. Here we have each role of the participant that is mapped to their own public address. And finally, we also map the choreography elements to their state. And we have an event order placed that later the front end will listen to when it happens. In the constructor, we first we give we assign each role with an ID, with the public address, and then we put the state for each element. So first element place order is enabled, and handover parcel, which comes after, is disabled. So the constructor will happen once we deploy the smart contract on the chain. Now we have the contract function, for example, the place order, which represent the choreography element we've seen before. And here, basically, this function will be called by the user from the outside, and they will pass the requested amount they want. First, we'll do a precondition. We'll check that the state is enabled, the current state that we're trying to call, and also the customer who's really calling this function. Afterward, we put the amount, we update the amount, we update the state of the contract, the process, and we update the state of the choreography elements. And then we enable the next element that we need to execute. Finally, we do the emission of the event so that now the retailer knows that basically the customer placed an order. So that's basically how it happens. First we have the state as they are. We have the placed order is enabled, and then the handover parcel is disabled because it depends on this element. Then after the customer does a transaction, the transaction is still not mined, it's still not placed into a block. So the states are still the same. But once the transaction is mined into a block, the state changes. So now place order is done, and the next element is enabled. So now it can get also executed. So how do we exactly do the mapping from choreography to smart contract? Currently, example we saw, we have one smart contract with the data and the control flow all built into one smart contract. However, we can have some different strategy. For example, data segregation, and here we decouple the data from the control flow. So in case we needed to deploy a new control flow, we don't need to do data migration. The second strategy is factory contract, and currently all the instances are represented also by one smart contract. So what we can do is we can use the factory contract to have separate smart contract for each instance, just like here. Now, combining both together, first, that's our first case. We have one smart contract for the entire data and control flow, or we can decouple it into one instance. Another option is we can have multiple smart contracts containing the data and control flow for each instance. And finally, we can have one control flow. However, we can have multiple data smart contracts for each instance. Well, the design decision here depends on the type of process we're having. Now let's look how we can implement this. So Hyperledger is a permissioned blockchain network. And we didn't use a public blockchain network because here we know who are the entities. And so in a Hyperledger, we have those components. It follows a modular architecture. We have the client, we have the peer, the order, and the ledger, and channel organization. So let's see how it works very fast. So first, the customer, the client, will broadcast their own transaction. For example, here, place order, and we publish to the peer. So peer is just basically just like a node that we saw before. The peers will run the contract and will verify that if it's valid or not. And then they will let the customer that it's valid, and then the customer will collect the endorsement of the peers. Afterwards, the customer will send us the order, which will build the block and then publish it back to the entire network. So for now, we need one channel that contains the entire data. And in this channel, we have the customer with their own peer and order. And that's the first organization, the customer organization. Secondly, we need another organization for the retailer with their own peer and order as well. So now that's basically what we have here. That's the choreography that's mapped to the architecture we have. However, let's imagine that we've added some more parties to the process. Now we have the banks, where the customer and the retailer pay each other through their own bank. So we have two banks, one bank for the customer and one bank for the retailer. So how do we solve this? We can also have a second channel for the banks, and to end up having an organization for bank 1 and for bank 2. And now we can see that the customer is a member of both organizations, also the retailer. So that's how our current choreography looks like now. So first part is basically based on the channel 1, since we have no banks here, and place order happens on chain, while the other can happen off chain. On channel 2, we have the banks, and then we see enough balance is basically that how we coded this in the smart contract, which happen on chain, and the transfer money also happen on chain. Finally, this is also on channel 1, and this also happens on chain. Now, we're going to talk about some advanced topics. So basically, we've been discussing about blockchain BPMN, and now these are some of the advanced topics that can be applied to this domain. So we'll talk about BPMN blockchain extension. So for now, we're just mapping from choreographies to blockchain directly. And for example, in this case, the entire choreography is placed on chain. Or for example, it could be placed on BPMS, traditional workflow engines. Or just like in our case, we can have some of the choreography elements on chain while the others happen off chain. So what we can do is we can also model. So now we're just doing the BPMN to blockchain, but we can also do the other way around. So we can come up with an extension to BPMN to the choreography that represents some blockchain elements. That's one of the future work. And then another advanced topic is flexible choreography design. So currently we have an imperative model. This is a static model. Once it's deployed, we can't change anything with it. So what we can do is we can have a declarative model where it's, the process is separated into different fragments, and then the combination of fragments will form the process during the runtime. So for example, we can have insertion. Here, for example, the customer chose to cancel the order. He can also choose to cancel the order after placing the order, and not exactly in this same position all the time. Or for example, we can have repetition. So here, for example, the retailer chose to deliver the product using 2 different logistic providers. And yeah, you can see it here. So, but that doesn't mean the combination can happen however we want. We still have a condition to follow. For example, here, the customer can't cancel the order after delivering the parcel. And yeah, that's basically it.